In this lecture, we will be talking about the computer programs that we can use in order to obtain good simulations and other analyses of dynamical systems. For that purpose, we will be going through a typical program integration, and we will be doing some examples starting from physical system representation to system simulation. We will be considering a particular environment, hoping that you will like this environment. Let me go over the different environments that you may want to consider for your own work. So there are several environments available for simulating dynamical systems. So when I talk about simulation, I mean something other than a system animation or what, but mostly the ability to write responses in the form of plots. You can do animations later. However, you will notice that they take a long time and they don't necessarily teach you much. They are there mostly for your entertainment. You will find them to be very useful when you want to show or communicate your work to other people in the company or university you will be working with. So I will concentrate mostly on plots. There are several software that you can consider. There is Matlab, there is Silab, there is Mathematica, as far as I'm concerned, I will teach you Silab because it's free. It is a competitor to Matlab, which is free to you as well. However, not free when you hit the corporate world. But you should feel free to use Matlab. The two tools are fairly close to each other. Silab installs in a record fast time and looks as follows. Let me erase it, and for the sole goal of bringing it back, comes as Silab 5.4.1, and it has been in existence for quite a while. The web page to access Silab is given here. Okay, www.silab.org. Silab's current business plan is to make free the basic Silab, and then probably make whatever modules are developed, specialized modules, less free. It is considered to be a tool for mathematics, engineering sciences, and automatic control engineering. If anything, I am teaching in Silab for the purpose of you having several tools available for you to choose from when time comes for you to make critical choices. So the Silab environment looks like this. You have the traditional directory environment here, an execution console here, a variable browser, and a command history. The console is where you enter everything we need. We can enter numbers, so we can say 2 plus 3, and we get 5. 2 times 3 is equal to 6. 5 times 7 is equal to 35, etc., etc. We can enter numbers and variables. A equals 3, B equals 5. 8 times B is equal to 15. We can enter them faster. For example, A equals 4, B equals 18. And what we get is that both of them are being defined, even though only B appears, since A is indeed equal to 4, and A plus B is properly equal to 22. You can enter matrices and vectors. So if we write W is equal to 1, 2, or 1, 3, 5, okay, you obtain this column vector. Now, if you write V is equal to 1, 2, 3, like this, it corresponds to the row vector, 1, 2, 3 instead. Now, the transpose of a vector, V prime, is the corresponding column vector. Such is W prime as a row vector. It gives a response to a transpose of the initial column vector. Next, we can enter matrices. A equals 3, 4, 4, 5, 6, 7, 7, 8, 9, 10, 11. Okay, and what you obtain is this. Now, A prime, the transpose of A, is simply written as you see here. And of course, A times W will return A times W as we've seen it before, since W is equal to, my apologies, to 135. Now, A times V, if you remember, V is a row vector. A times V will return an error. However, V times A will return an answer because the dimensions are compatible. Okay, V is a row, A is a matrix. V has 3 entries, A has 3 times 3 entries. Therefore, we are fine. Next, besides variables that are numerical, we can also define symbolic variables. For example, S is equal to the symbol S. Okay. Now, what we have here is S becoming the variable. Now, we could define A is equal to the symbol S if we wanted to. Okay. And then we could say S is S, A is S, and S minus A equals, well, 0. Okay. But S minus 3 gives you a polynomial. Okay. And now S times S, so we could say that S times S is equal to S squared. Okay. Likewise, by the way, we could have defined instead S is equal to person D. Okay. And now that doesn't work. All right. So we insist on saying that the person S is the most important, okay, and it corresponds often to the Laplace variable or to a polynomial, okay. Let's see if person X exists. So person X does not exist, okay. So it looks like the Laplace variable S is very special in this environment, okay. And we can write polynomials like S cubed plus S squared plus S plus 1, and we will obtain the same polynomial, though the powers of S have been written in growing powers of S instead of diminishing powers of S. Okay. Whenever you don't know how to answer questions, you can always refer to the particular thing here. And for example, if we take root, okay, I want to compute the roots of a polynomial. Well, it doesn't seem to be very particularly useful. However, here we have root properties. No, that doesn't give us everything. So we're going to try something else, which is roots. we see that roots is the roots of polynomial. Okay, so if we compute the roots of the particular polynomial we have here, s cubed plus s squared plus s plus 1, okay, we'll get the roots written as plus I minus I and 1. You can see that there is a 10 to the minus 16 that appears here, okay, but that's okay, it just is a numerical error, okay. Nevertheless, numerical errors ought to be looked at very seriously when you turn your attention to a more engineering-oriented thing when you deal with a real object such as a full aircraft. Next, you can define variables, okay. P is equal to, you can define polynomial variables, okay. So P is equal to s cubed plus s squared plus s plus 1 gets you this thing, so you can manipulate these polynomials, okay. Now you can divide polynomials with each other. So for example, you can write system or transfer function is equal to 1 plus s divided by 1 plus 2 times s plus 3 times s squared. Okay, what we get out of this? Well, you get, oh, my mistake, I forgot the multiply here, but eventually what you obtain is the ratio of two polynomials, and therefore what you have here is literally a transfer function. Okay, so it is the transfer function of a system, God knows which one, I'll let you think about it, but it is the transfer function of a system. And so with that, we can plot lots of interesting things about this system. Okay, so for example, the impulse. So for that, in order to understand how we're going to do that, we go to a particular function here named csim. Okay, it's about simulating a system. And what we see is that the way it works is normally if you are given a system, okay, for example this one, okay, and we are given a input which is u, okay, it's the input to the system, and we have a definition of time, okay, we can use the csim function to get the response of the system to a particular input, okay. The particular input here, the particular system here can be defined as a linear system, we will see later, in various forms, including a transfer function, or what we will see later is a linear dynamical system expressed in state space form. Okay, so let's write how this works here. Okay, so we will use this expression to get the answer to the step response, okay, to the particular thing we're interested in. So I copy this, okay, and hold on a second. I will define, oh, I need to define time, okay. So time is just a simple vector, okay. In this case, so I copy it here. You will see what it looks like, okay. It's a way to express vectors, which is fairly simple and very simple and very the same as Matlab notation, whereby the response is the vector is a row vector, okay, which is a row vector made of a bunch of entries spaced by 0.05, starting at 0 and ending at 5. Okay, so that's a useful way to write tons of different things at a very low price. If I go back to the help console, okay, what they do is they use that particular formula in order to plot the step response of the particular system. Now, I don't like their system, I prefer mine. Therefore, what I will do is I will go to the console and I will use it for my particular transfer function itself there. So my particular transfer function is, let's see, hold on a second here, csim, okay, so we will use that thing, so we have csim, okay, so I will use here the system transf, okay, which is the transfer function I defined before. And let's see what that gives. So plot2d is a plot function, okay, which has to plot things in 2 dimensions. csim is the simulation that will take a step over a certain time t for the system transf. Okay, so if I do this, I enter the command and I get a warning. Now it says that it gives me a warning, which is the first one is assumed to be an argument, and I have absolutely no problem with that. Okay, what you see is that I get a curve. Okay, and that curve literally describes what the system response is. And as you can see, it is a nice response that starts at 0 and then reaches, in that case, a little bit more than 1. Now, is it normal that it gets more than 1? Well, let's see if what the system does afterwards, because it's kind of sluggish, okay, and 5 doesn't seem to be long enough. So for that purpose, what I can do is call this back, okay, and define t to be 10 instead of 5. Okay, I skip, when I put a semicolon, it prevents me from having t displayed like it did before. And what we're going to do is the same operation. Okay, and then now what it did is that what it does is it plots the response of the system. Now we can see a lot more interesting things. That is, the system seems to be returning to 1. T is not long enough, so we're going to change that still. Okay, and we're going to make it 20. That should kill everything and give us a nice response altogether. Okay, and when we go there, what we see is now a nice response that indeed seems to be settling at 1. Now, remember, trans is this, okay? And what I'm asking you is to think about why the step response of this is indeed equal to 1. Remember, the way to do this is by using first the Laplace transform of the system, of the impulse, of the step, okay, multiplying the system by step, and then use the initial or the final value theorem. Okay, so let's go about it. Let's see if this system should have been equal to 1. For that, let me erase here and delete this system and plot so the system, which was s plus 1 divided by s squared plus 3s, I think it was plus 2s plus 3, 2s plus 3. Let's go quickly to Matlab, to Silab, sorry. And yes, 3s squared. Okay, so we go back to our plot environment, and so we add the 3s squared. Okay, the step is 1 over s, okay, in the Laplace domain. So we multiply this by 1 over s, and then we take, in order to get the value of this system at infinity, we compute the limit when s tends towards infinity, s tends towards 0 of s times this guy. Okay, we get that this s, let s go away, remains this guy, and when this guy gets down to 0, then well, then we have a mistake. Okay, and the reason is because I didn't say that this one 1 over s squared plus 2s plus 3s cubed. In fact, let's redo that example. If we go back to the example in written, okay, we write that the system is s plus 1 divided by 1 plus 2s plus 3s squared. Okay, so now when we have a step, okay, a step in the in the frequency domain is 1 over s. Okay, so we multiply this by 1 over s. And now if we want the value when t tends towards infinity of this, we have to take this multiplied by s, and we take the limit when s tends towards 0 according to the one of the value theorems, okay, initial or final value theorem. Okay, we get the limit when s goes to 0 of that. This guy and this guy go away. All these guys with s goes away, and there remains that this is equal to 1. Okay, so we know that the Matlab, the Silab answer, I mean, it looks curiously like Matlab. I started medication with Matlab, and I switched to Silab now because I want to be independent. I have my standalone version of Silab. I don't have to hook to the system to get there. And what I see is that the response of the system is indeed what it should be. Okay. Now let's see how things work for the impulse instead. Okay. So for that, we're going to do impulse. So impulse seems to be referring back to csim. Okay. And it says we use impulse without an e. Okay, so we go back to our example, and we write, instead of step, impulse without an e. Okay, in here. And what we get is that the answer to the system is now this one. Okay, so the system starts at 0, jumps immediately to some value, 0.35 or so, okay, and then responds by going back to 0 like it should do, because it's a stable system. Okay, so now the problem is that it plots on the same window as this guy. So what you can do is you can open a new figure, okay, or and so now you have two figures, figure 0 and figure 1, or you can clean figure 0. Okay, so if you clean figure 0, then that figure goes away, and you are left with figure 1, and we can now plot in that figure the response of the system. Now it turns out that the background has become gray. I don't control all the variables here, but the response of the system, the impulse response of the system, now shows on its own. Okay. All right. So now we can use csim in a smarter way. As you have noticed, if we go to csim, okay, we can put specific inputs. Okay. So so we don't need to put necessarily an impulse in here, okay, we can use other things, okay, and in particular we can use we can use something instead of impulse, okay. Now when the system, so we need to look briefly, we always need to look briefly at this thing. However, it really looks like what we can do is replace impulse by some other quantity. Okay, so we go back to the system, and what we're going to do is we're going to define an input which is not an impulse. So we go back here and we're going to write input, so we're going to call it f. Okay, it's a time function, is equal to, and we're going to say sine of t. Okay, now what that gives is the sinus answer to t when t is taken as expressed in degrees. Okay, remember that t is from 0 to 20, so sine of t will be from 0 to 1 over the interval where t ranges from 0 to 20. Okay, so what we could do is, for example, we can do look at the input in the first. Okay, and what we're going to do is we're going to say plot 2D of t and f. Let's see what happens. Okay, so we have a problem. Okay, so let's say f prime. And what shows is, well, here's what shows. Okay, so what does that mean? Not sure. Okay, but oh, I see. Okay, so we have t prime, f prime. So this is the number of points involved. All right, so it's the number of points involved. And this is just t as a function of t. We just plot t here, which is from 0 to 20. And f looks like a sinusoid. Okay, so now we don't seem to be using plot 2D very well. So we're gonna do, we're gonna look at it, okay, and see how we can use it best, okay. So here it seems that our only mistake was to plot this thing the wrong way. We introduced a vector, so let's not introduce a vector, okay. And we're gonna remove this guy here. And we're going to remove the primes, okay? They seem to be like troublemakers, and see what happens, okay? So the problem is we did not put a new picture, so the sinus is properly plotted, but over too small an interval. So we're going to erase that picture and then do it again. And now that since we have erased the picture, we get finally what we want, which is the value of f of t as t grows from 0 to 20, and f is the sinusoid, the sine of t. So why are we doing that? Because now that we have the proper input, okay, we're going to put it inside the input for our system, okay? So if you remember, we use two functions. We use the plot function to show, we use the plot function to show the response of the system, and system to simulate the system. So now what we're going to do is we're going to remove this guy, okay, and we're going to put f instead. So remember, f is the input, which is a sinusoid. And we are also going to clean up this picture, because we know that otherwise things will get plotted on top of each other. And we call this function. Let's see what happens. It takes a little while to compute, but eventually we get the following answer. Okay, the system starts at 0 and then starts oscillating. Okay, and you see that the oscillation is not quite regular, and that's because we have a transient followed by slowly the establishment of a steady state regime. We can see that steady state regime if we change f and t, okay, by first defining t as, say, operating over, instead of 0, 20, 0, 50 or 60, okay, and then choosing f. You can use the arrows to call the previous orders. Okay, you get f equal to sine of t, and then we can do the plot 2D thing. Now, since again that picture is going to be confusing, okay, we're going to plot it in a brand new picture, and the brand new picture will give us, well, something when the simulation is finished. Okay, it takes time to do these calculations, but it gives us the response of the system after a little while. There we go. And here's what you see. You see much better the transient, followed by a steady state response. Instead of using f equals sine t, we could use f is equal to cosine t. Okay? So if you use f equals cosine t, you would get another answer that I'm going to plot on top of the previous one. And the figure should appear pretty soon, when the computations are finished. But again, it takes a little while. These are like painful computations. Although I'm a little bit surprised by how much time it takes this time. I'm going to show them. You see that the response of the system when I use the cosine is somewhat different from that where I use the sine. Okay, but eventually you get that these two sinusoids and cosines are, the response are basically 90 degrees out of phase from each other, as they should. Okay, because of what we told you when we computed the forced response of a linear system. Okay, we could use a ramp instead. Okay, so we could write f is equal to 3 times t. Okay, or f is equal to t. Okay, that would be a standard ramp. Okay, now let me clean the window here, and now let me do the same plot function. Okay, the response is very fast and carries quite a bit of information. I don't know how to zoom. Okay, hold on a second. So let me try and zoom again. An axis box. Oh, I see. Okay, so we can zoom in, but let's go back. Tools. So we're gonna, okay, so we zoomed out. Let's see in more detail what that does. Okay, let's zoom in more, because what I want is eventually to have more details. Okay, so what you see is that the response of the system when we get close enough is that of a ramp indeed, but the ramp is kind of slow. All right, but eventually the system follows the ramp, and I ask you to understand why this happens. Okay, so what we'll do is go back to the representation of the system. Instead of a ramp, you can use tons of other inputs. You could define a particular input. Okay, you could define, for example, your input to be a window. Okay, you just have to program it in. Okay, now what I would like to do is cover an example, okay, and see how that example moves from figure to math to Silab. So I'm going to erase all this and go back to the environment, and that environment, I'm going to use a reasonably good font. I'm going to look at, well, deliberately, I'm going to look at the response of a system which looks like this. Okay. So I'm sorry because we have all these masses and springs. Okay. But I mean, they are easy to model, and that's why we use them. Okay. So here is the spring. Okay. As usual, here is the mass, and here is the dashpot. Now we assume there is also a force F, and we are looking at, for change, the speed response. Okay, so we're looking for how the system responds, and we're going to look at x dot, okay, which we're going to call also v. So the equations of motion for this system are well known. If this is the k, the spring constant, and this is mu, the viscosity constant, then we can introduce the differential equation, which we know with m, which is mx double dot is equal to minus kx minus mu times x dot. Now we write the initial condition. We're going to say x of 0 is equal to 0, x of 1 is equal to, x dot of 0 is equal to 0, and then we get that under this condition, the Laplace equivalent to this will be x times, oh, and I forgot the force, F. Okay, so we get that x times ms squared plus kx plus mu s, and that x has no reason to be here, okay, is equal to F, which leads us to x is equal to F divided by ms squared plus k plus mu s. Okay, now since we're interested in x dot, we have that x dot equals s times x, and therefore x dot is equal to s divided by ms squared plus k plus mu s times f. Now we're going to choose m is equal to 1, k is equal to 5, and mu is equal to 0.2, okay, for the sake of it. Now, if this is so, okay, then our transfer function will be x dot is equal to s divided, I'm going to call it v, okay, you add the hats wherever you need to, is equal to s squared plus 0.2 s plus 5. Okay, now what we do is we go to the Silab. Okay, I'm gonna make it a little smaller so that I can see the electronic environment. Oops, I can see my figure. Okay, I'll make it as big as I can. And I will certainly make that window smaller because I don't really need it for the purpose of introducing my transfer function, okay, which I will call h. H is equal to s divided by s squared plus 0.2 s times s plus 5. Now, like I could before, I can do the impulse of h. Now, what I'm going to do is first I'm going to erase that window and then go back to this by using the same elements as before, okay, which means that I'm going to use the same command. Again, I'm very much for template matching when it comes to typing this. Remember, this is the old transfer function, so now I'm going to call it H. The sysim impulse is going to be the impulse, okay, and why not? We're going to simulate it over a long time t, which ranges from 0 to 60. Boom, let's go and see what happens. Well, here's what happens, okay, not a bad thing actually. You see the system starts at 0.8, only almost 1, and you know, I will ask you to think about why, okay, and then the system oscillates and slowly dumps out to 0, okay. This is typical of a system which is stable, and what you see is that the response is very clean, okay, and dumps out to 0. Now, if you do the step response of the system instead, which is the response to a particular input, to a particular step, okay, you will get that we replace the impulse by a step, okay, and the answer we will get, which will be plotted on the same picture, now looks like, oh, it's dying out to 0. Okay, so does this make sense? First of all, let's replot this thing without the previous impulse response on it, okay, and sure enough, the thing comes back with a response which looks seriously like the impulse response. Now, it's normal that the step of a system die down to 0. Again, I let you use the initial and final value theorem to show that. However, what we could do is also write that H1 is equal to H is equal to H divided by S. In which case, we get that H1 is 1 over this guy, and since we divided by S, what we already took is the position instead of the speed of the system. And if we do the step of H1 instead of the step of H, what you're going to see is that the response is very different. Okay, it has not computed yet. I don't think it has, at least. Let's see. Ah, yes, but here's what happened. I have not changed H into H1. So now I have changed H into H1. Things should be nicer. And sure enough, we should get something different. Yes! The step response of H1, which is the step response of the position, goes here. And by the way, it doesn't go to 1, it goes to 0.2 or something. Whereas the step response of H goes here. And when you think about it, that's normal. This is the position, this is the speed. When you look at the derivative of the position, it eventually flattens out to 0. And that's what it does. Okay? So, likewise, you can respond to other inputs. So we're going to say F. We're going to write it as cosine of t. Okay, remember t goes plus sine of 3 times t. Okay, should work. There's no reason why not. Okay, we're gonna do we're gonna clean well, we're gonna take another figure, okay, and we're gonna say that we're gonna plot t comma f, uppercase f, okay, sorry, uppercase f, okay, let's go and try that again. T comma f, what we get is that the response of the system is something like this, okay? So it's, well, it swings around a little bit, okay? What you can see is that it has a low frequency component and a high frequency component, which sort of corresponds to the fact that we have the sum of 2 oscillations, okay? The 3 times t and t, okay? We could do instead f is equal to that plus 10 times that, or 5 times that, and we're going to see that it's going to be a little bit different, okay? If I call back this second picture, which is here, I'm going to kill them, and now I can do the same plot, if I call a new figure, okay, so let's go here, and what we can do is plot finally this in order to get the response of the system, which now looks like it has a little bit of a slow speed component and a lot of a 3 times t component. Okay, so that is 3 radians per second component. Okay, so if we go back to defining f as that of sine t plus 3 plus 5 times 3 times t. Okay, so we have like a more or less balanced force that has 2 components. We can certainly call the same plot 2D thing that we used before and get a brand new set of figures for the response of the system. Okay, so we're gonna say we're gonna clear that picture and call this simulation. Now, if we call the simulation, remember that we can call sysim, okay, and we can plot step. And instead of step, we're going to plot the input, which is f, okay, and we will get the same answer now, which is we get a different answer for the time response of the system, okay, and the answer of the time response of the system will look like, wait a minute. Well, it looks like this. Okay, so again, there is a transient, and then eventually some kind of steady state appears, which is the sum of 2 sinusoids. Okay, you can look at using the previous lecture. You can look at how and why this is the answer, and you can even like plot this answer. We can in fact compute this answer. Okay, the steady state part of the response. Okay, we can also plot the transient, and it's a little bit more complicated, but we can do it using the previous lectures. Okay, now I would like to try something. Okay, template matching only has some value. Okay, so it's not forbidden to be a little creative, which is what we're going to do now by removing a bunch of things, okay, including a bunch of things like that. Okay, so it becomes simpler, and what I'm going to do is kill the picture to see if we can get the same answer. When you try things out, it doesn't always work, but in this case it did. Okay, as you see, it computes something. Okay, it's a simpler expression, and it works too. It's just you plot this and the response of the system. Okay, so we're still waiting. Okay, and that's what we get. Okay, so it's the same response, and it's just computed using a simpler command structure. Okay, so at this point, I think I want to stop here and and we'll discuss how all these computations work in the classroom. We will consider other computations as well according to your questions. Thank you.